to kind of set this all up, we'll think about just random variables in general and then talk about more specifics. So a random variable is just a numerical description of the outcome of an experiment. So all a random variable is that we know we're going to have this experiment being run. We don't know what the outcome is. This could be as simple as asking somebody what their favorite color is, right? And then having some numeric, actually, that would make sense, but we could put a numerical value to the like our to it. But think about maybe I'm asking somebody how tall they are, and then I'm going to record it. Now I know the range of possible experimental outcomes for human height, but I don't know that one specific random person's height. Mhm. So we're going to have two different kind of categories, discrete and continuous, for these random variables. So discrete, similar to what we've already talked about. In fact, here, let's see, I don't know if I have it, but we said discrete is going to be where I see like integer values quite often. So 1, 2, 3, but I can't see 3.495. Continuous is where I can see any value, right? Truly, it's like an infinite number of possible values. I could see 26.3192, right? So the way we're going to notate these random variables is using this capital letter X. It's kind of similar to what we talked about last chapter, like thinking about like, I'm interested in a certain event. Here, our event is kind of this variable X or this random variable X. Okay. We're then going to think about, okay, I have this experiment. Maybe I am like selecting random people and asking what their height is, but I'm asking more than one person, right? I'm asking one person, then I'm asking two people, et cetera, et cetera. So um, we would kind of notate these as smaller lowercase x with a subscript 1. That's the outcome I saw from the first run of this experiment, right? So the first person I asked, what was their height? Second person I asked, what was their height, et cetera, et cetera. Okay. So that's the notation that we'll be using. Um, you know, Usually we'll look at discrete random variables that have kind of a smaller or finite number of values. Once again, this is kind of discrete where we don't see anything in between. So how many times last week did you engage in athletic activities, or how many days did you do such and such, or um, right? I can only see the actual integer values. And then our continuous random variables, once again, I can see any value, annual income, interest rates, kind of very similar to what we were talking about before with just talking about discrete and continuous values. Similar, it's just applied to a random variable. So, some different ones we could think about, like family size, right? So it has the number of dependents that are on a tax return. Can't have 1.5. It's either 0, 1, 2, right? So it's going to be discrete. What if I select a person at random? I want to know what's the distance to the nearest store. So one of the big things right now is like food deserts. So it's areas where there's not high quality food in a nearby kind of like a walkable area. And so maybe this is the distance they are from to a store or a grocery store. That could be 2.19758 miles, right? That would be continuous. What if we have kind of this example where it's kind of like we can sometimes convert non-numerical values? So here I've got owning a dog or a cat. So this is where I started to say the example of asking somebody their favorite color. Well, you could just give every color a number similar to here. Owning no pet is a 1, dog only 2, cat only 3, cats and dogs 4. So this is a discrete example. I tend to be in this category with a value of 4. So if you hear filming some of these from my office at home. So if you hear cats or dogs, that's why. Uh, so anyways, so we've got discrete, we've got continuous random variables. We then want to think about, okay, I asked someone their height, but I know that different values are more likely. If I ask a random person their height, I know that seeing the value of 5'8" is probably going to be a lot more likely than seeing, I don't know, 6'8", right? So there with these random variables, just like a variable, they're going to have a distribution. It's just that their distribution will be in a form of a probability. Well, this starts to make sense. Remember, the last chapter I said relative frequencies, it's very similar to probabilities. Well, what can we do with relative frequencies back in chapter 2? We can graph them. We can come up with a probability distribution. Yeah. Now you can do this with a visual, like a graph. We can also kind of put a function to it. In fact, when we talk about binomial and Poisson distributions or variables later on, they'll have very specific functions, but we can always kind of create a nice visual to go along with it. So any random variable is going to have a probability mass function that tells you for different values of x, here's the probability they occur, right? So in my height example, the probability of seeing 5'8" going to be a lot different than seeing 6'8" okay? All right, so this probability mass function, essentially like for every possible x value, there will be a probability that the random variable x takes on that value. So there's like an x and y pair. So you almost think about it as, well, what does this probability have to be between? It's follows all of our like principles from before. If I'm looking at the probability that something occurs, for instance, maybe I'm interested in what's the probability that I select someone at random that their height they report, I don't know, 1 feet 3 inches. Okay, if we're talking about an adult human, I know that probability that there's no one that's that tall. Or I don't know, maybe I can't imagine there's no three, maybe they report 3 inches. Well, the probability we see somebody 3 inches tall is it doesn't occur. So 0 out of however many births there are. So 0. So the lowest probability we can see is 0. The highest probability would be 1, right? Now, in practice, often we don't see that. Those wouldn't be very interesting examples. If if you had the probability of the random variable taking on a certain value being equal to 1, okay, there's no more work to be done. Like we automatically know the outcome of that experiment, or that random variable. Now if we add up the probability of every possible x value, so this is the probability if I select someone at random, they report that they are 1 inch tall, 2 inch, 3 inch, all the way up to I'm the tallest person, 9 feet. I don't think anyone's been ever taller than that, but like we go up to 10 feet. If I add up all those probabilities, that should cover every single possible experimental outcome. We said our experimental outcomes, the probabilities of them add up to 1. And we saw that in our contingency tables even. Okay. Our cumulative mass function, we did talk about this kind of back in chapter 2 a little bit. We were talking about cumulative relative frequencies. And it's because we also are going to have cumulative mass functions, right? Or we might be interested in, okay, what's the probability that this random variable x takes on a specific x value or anything less than that? So our cumulative mass function, whatever value we're interested in, we're thinking about including that equality, okay? So what's the probability it's this value or anything less than that? As we get to really small values of x, right, that cumulative mass function is getting closer and closer to 0. Once we get to larger and larger values, it's getting closer to 1. So this is the idea of, okay, what's the probability that somebody is selected at random is 5 feet or lower, 5 foot taller or smaller? Pretty low, right? Pretty close to 0. I mean, it's not 0, but it's pretty low. But as I start to increase, okay, what's the probability that I see the recorded response be 5'6" or lower? Well, that's a little bit higher. 5'10" or lower, a little bit higher. By the time I get up to 8 feet, I'm basically at 1, right? So for really large values of x, this cumulative mass function will approach 1. So this is kind of a stupid example, but I think, I don't know, I think it sets it up, and it's kind of a business related example. So we're thinking about, let's say we've got some company data, and I looked at the last 35 years, okay? And how many new hires they had every single year. So I was kind of worried maybe something about like expansion of this company or employee turnover. And so all I'm going to do is take those frequencies, right? How do I turn a frequency into a probability? Or how do I turn it into a relative frequency? I simply take that frequency and divide it by the total. So here, 2 out of 35 years, oh, sorry, 2 out of 35 years, they had 1 new hire, or a probability of 0.606. In 7 of the years, they had 3 new hires, so 7 out of 35, 0.2. Right? Wait, these numbers don't match up. Time out. uh, well, no, oh no, this worked. Sorry, I'm doing bad mental math in my head. I was like, hey, wait, okay, sorry. Um, so we've got the frequency divided by that total number of observations gives us that probability, right? We kind of done, like I said, we've really looked at this already with frequencies and relative frequencies. It's just now those relative frequencies we're specifically thinking about being probabilities of different x values occurring. I could then graph those, right? I just use my different values for that variable, that possible experimental outcomes as my x-axis, the associated probabilities as my y-axis. It looks very similar to what we were doing before, like building a histogram. I can kind of now quickly see, oh, okay, well, if I'm thinking about this next year, what's the likelihood they have 3 or 4 new hires? Relatively high. What's the probability that they hire 10 people? No, they won't, right? They never have, at least been before. And so using these empirically assigned probabilities, we would think that probability is 0. Okay, so here's my probability distribution. So how do I find the mean of a discrete random variable? So it's going to go back to something I kind of already talked about. So the mean of a discrete random variable, we sometimes give a slightly different name to, which is the expected value. And that's because it hasn't occurred. We're only looking at the outcomes of experiments that have been run, right? So this is really not like 100% going to be the mean. Like it's based off of the previous outcomes. So it's the expected value of the next time this experiment is run. So generally we'll write this as kind of using mu, still using that same Greek letter, but subscript x kind of representing that this is a random variable x, or the expected value of this random variable x. For a discrete random variable, right, all we're going to do is go through, take every single x value, multiply it by the probability it occurs. Oops, if I can get this to, there we go, and then add them all up, right? Just like a weighted mean, right? So here, if I think back to like my weighted mean example, where I kind of had like the frequency, excuse me, here, oops, my frequencies are going to be the weights, or the probabilities are the weights here. Well, what is the probability? Sorry, what is the sum of the probability of every single possible outcome? My denominator here will always be 1. Right? So then I'm just simply left with the mean is every x value times the probability it occurs. Okay. What's another way of thinking about this? I think that's all we really need to say here. I think it's really closely related to what we were doing with the weighted mean. It's just now we don't have to worry about the denominator because the sum of our weights should always be 1. So if I'm thinking about my example here, how would I find the mean or the expected value for new hires? Well, I go through every single value, take it, multiply it by its probability. So 0 times 0 plus 1 times 0.06 plus 2 times 0.03 plus 3 times 0.2, all the way down to the very last kind of outcome. Now here, the ones where the probability is 0, do I really need to add those in? No, right? Adding 0 is not going to change anything. So to save myself a little bit of time, I really could just look at the values 1 through 9. But if I did include those values, just in case, I don't know, I get new data and these probabilities get updated, it would be kind of the entire process written out. So I get about 5.14 here, right? So nothing really new. We're not reinventing the wheel. Variance, same kind of idea. How do we calculate the variance of any variable? Well, here, this is the variance of a random variable, right? So to kind of relate this, oops, I want to make sure we're staying on the right slide here. There we go. And I'm going to stop share. Okay. So when I'm calculating the variance, and I think here, I need to rotate. There we go. So if I wanted to calculate a weighted variance, before we were doing this, we said, okay, I would add up all the x values multiplied by their weights divided by, or sorry, this is my equation for the mean, right? We said the sum of our weights is now 1, so we just have our numerator. For our variance, we were looking at the sum of the difference of that x value with the mean multiplied by the weights divided by the sum of our weights. Well, once again, the sum of our weights will be equal to 1. We don't have to worry about that denominator, right? What are our weights now? Just the probability that x is equal to that specific value. So when it comes to that variance, it's a little bit easier than even what we were doing with a weighted variance example. Right? Also, same kind of rules apply. Our standard deviation will simply be the square root of our variance. Okay, so nothing crazy here. So if we look at our data for new hires, what would I do? Well, I'd go through the very first observation value, or sorry, observation, the first value, possible experimental outcome value, 0 minus the mean of 5.14, square it, multiply it by the probability 0 occurs. Once again, whenever we have these probabilities of 0 occurring, do we really need to use this? No, right? But then go to the next outcome, 1 minus the mean, square that deviation from the mean, multiply it by probability that I see that value of 1. Add to that the next value, 2, deviation, it's deviation from the mean squared, multiply by the probability that I see 2 occur, right? So on and so forth, all the way through every single value. Here I end up finding that the variance is kind of similar to the mean, just a weird example where that's true, but 5.38. How would I find the standard deviation? I just take the square root of that, okay? So here's some really easy toy examples that we'll kind of work through. Thinking about what's the mean bonus amount. So this is where also I want to start to go into a little more like intuition when we're looking at problems and not getting too lost in the formulas. So here, if I wanted to know what's the expected value, what's the mean bonus amount? So this is like some crazy crazy big company and they're giving millions of dollars out in bonuses. This is a goofy example, but stay with me, right? So 10 million, 6 million, 3 million, 0 million. Okay. Well, I need to go through, define the mean. I'll add up every single possible X value times the probability it occurs. But if I look at these, I mean, so what are the most likely outcomes? 6 and 3 million. 10 million is a little less likely than 0. I doubt, right? Just looking at eyeballing this, remember, these are weights. These probabilities are weights. So 3 and 6 are going to be carrying most of the weight in determining what this mean is. My guess is that the mean's somewhere between 3 and 6. So A and B probably seem a little bit too low, even on its face, right? Before I even do the calculation. But to do the actual calculation, I'll go through, take 10 times 0.15. So that's what, 1.5 million. 6 times 0.25, another 1.5. I'm at 3 million. 3 times 0.4. 1.2, so now I'm at 4.2 million. 0 times anything is 0. So I should get, oops, the answer is 4.2 million. Right? What if I wanted to find the variance? Now, using some things we talked about before, first of all, which of these can I rule out right away? We know the variance has to be positive. B doesn't make any sense at all. Okay. Now, other than that, it's kind of hard to really see, think about where the variance is, but we know it can't be negative. So how do we, what do? Well, we go through this, take that X value, subtract the mean of 4.2 we found in the previous slide, square it, multiply it by 0.15, write that number down. And take the next value, 6 minus the mean of 4.2, square it, multiply it by the probability it occurs 0.25, write that number down. Do that for all 4 values, and then, whoops, add them all up. Right? So if we actually go ahead and do this, I'll show you a way that you can kind of shortcut this. So I didn't include this in the slides, but well, let's select the whole thing. I'll actually even show you how to do the weighted variance as well. We'll zoom in. So I just have a blank open Excel file. So that was what was in the slides. So how do I find my weighted variance? Or sorry, let's do my weighted mean first. Right? Now, if I was doing this, instead of typing this all out, what I could do is say, okay, look, take this times this plus this X value times the probability it occurs, so on and so forth. But let's say instead of 4 outcomes, I had like 40. Man, I really don't want to go through and do that, type that out or just select that those cell references that many times. So what I'm going to do is just kind of create this column where I'm multiplying that X value by its probability of occurring. So I'm going to take the X value, multiply it by the probability it occurs. I'm then going to copy this down so that I can do that for every single one of these. Then once I'm done, all I simply need to do is use that sum function and add all of those up. Remember, we don't have a denominator anymore, so we're done. Our numerator, the sum of the x values times the probability they occur. Once we add those up, we should have our weighted mean. Same kind of idea with my weighted variance. What I could do is say, okay, look, take first value of 10 million minus my mean, square it, multiply it by the probability it occurs, do that for every single possible outcome. With 4, this is doable. With 40, this is going to take me forever. So what can I do? I'm going to create this column where I find that deviation from the mean squared. I then multiply it by my weight, which is the probability that x takes on, come on, that x takes on that specific x value. Okay. So I'm going to go through, take the x value, subtract the mean. Now I could type it out. I'm going to just show you just to get more practice using cell references. I'll select that cell reference, square that deviation, multiply it by the probability I see 10 million occur. Now, when I copy this down, I want the probability and the x values to update, but I want to keep using that same weighted mean. So once again, we can freeze that cell reference, put $ in front of that row and column heading. I manually did this. If you highlighted it, remember it's Command T, F4 on it, or sorry, Command T on a Mac, F4 on a PC. Hit Enter. Now when I drag this down, now to get my weighted variance, I simply add up the sum of those deviations squared times their weights. So use the sum function and get 9.96. Okay. To be complete, what's my weighted standard deviation? That's simply going to be take the square root of my variance. That's how you do it. For your homeworks, exams, everything, you're gonna be able to use Excel. I would honestly get comfortable and try to get good at using Excel to solve one like this. It just makes it easier. You don't make a mistake on your calculator. But if you want to use a calculator, by all means, you can do that as well. Just I want to show you with these examples specifically how you could use Excel to kind of make your life a little bit easier. Okay. Now kind of a little step aside, just because it's kind of related to what we'll talk about here next. But let's assume, thinking about probabilities, that we've got, I don't know, what's the probability of 2 people in this class? Let me see what number I used. I think I used 40. So let's say I had a class of 40 students, right? I think we're slightly smaller than that, but we'll use 40 for the sake of this example. What's the probability out of 40 people in this class that 2 people would have the same birthday? So let X be the event that 2 or more people have the same birthday. So we're just interested, is there at least 2 people who have the same birthday? So if every day is equally as likely, right? If I'm choosing a person at random, the probability that they're born on January 24th is the same as they're born on February 2nd. Right? I think that's technically not quite true. I think some months have higher birth rates than others, but for the sake of this example, it's pretty close. And we're going to assume births are independent. So like we don't have any twins in the class. No one's parents were, trying to coordinate when they had kids so that they had built in or had some neighborhood friends or anything. Everything's independent. So initially, if you ask most people this question, out of 40 people, you'd be like, yeah, it seems very unlikely that 2 people would have the same birthday. Okay? Also, how many people, how big would the room need to get in order for us to see 2 people have the same birthday, right? Maybe think about it. If we have 365 people, it's possible everybody has a unique birthday. So most people would say like, oh, you need more than 75 for sure. So we can actually work through this. So let's use some of the old probability laws that we talked about to kind of think our way through this. So if I want to know the probability that 2 people have the same birthday, I could rewrite that as 1 minus the probability that nobody has the same birthday, right? Or the complement of that. So the complement of 2 or more people having the same birthday would mean, well, what's the complement of that? Nobody having the same birthday. Excuse me. So now I'm going to think about, okay, what's the probability that nobody has the same birthday? Well, that would be, if I asked the first person what their birthday was, what's the probability they have a unique birthday? or that no previous person that I've looked at yet in this class has that birthday. Well, there's 365 possible days. Any day that their birthday's on, they're guaranteed that first person has a unique birthday. What about the second person? Well, the only way they can't have, or that, sorry, the only way they have a unique birthday, or it's not the same as someone we previously looked at, is if it's on one of the other 364 days. So you can think about there's only 364 remaining possible days for them to have a unique birthday out of 365. So the probability that second person has a unique birthday, pretty high. Or, right, the number of people minus one, because the very first person had a unique birthday, it can't be that day out of the total possible days, 365. And then the third person, well, there's now 363 remaining days that would give them a unique birthday. We could kind of extend this all the way down to 40 students for the 40th person. Probably the 40th person has a unique birthday would be what, 300, 20, what, 326, right? Out of 365. So we could kind of go through. Now, if every event is independent, what's the probability that nobody has the same birthday? That would be the probability that the first person has a unique birthday times the probability the second person has a unique birthday times the probability that the third person, right? Because they're independent. So to find the intersection of the two, that every single person has a unique birthday, that person one and person two, three, and person three, and person four have a unique birthday, just multiply those probabilities by each other, right? So we would take 365, multiply that down. And sorry, this was the first person, second person, all the way down to that 40th person. Okay. All right. So actually, I think that there's a small, I was typing this out. This technically should be 326, I believe. And here I changed it to 30. Oh, we'll play around with this. I think this is for 40 people, but we'll see. All right. Sorry about that. I think I switched it up for different class sizes. So here I could find the probability that nobody has the same birthday. If I rewrite that, well, I'll actually find that it's something I can rewrite it like this. Now we haven't talked about factorials yet, but all of factorials is to be kind of a good introduction to when we talk about them is you would start with this value, 365, and multiply all the way down to the value of 1. So this is going to be a very large number, right? Now we'll talk about ways that we can kind of deal with that here. But if I were able to compute this, the probability that in a class of 40 people, nobody has the same birthday is right around 30%, which means that that's the probability that nobody has a unique birthday. So the probability that someone does have the same birthday would be 1 minus that. So there's actually a pretty high likelihood that in a room of 40, 2 people have the same birthday. In fact, you can back out what room size you would need in order to get that probability to just break over 0.5. So at 22 people, it's not quite, at 22 people, it's not quite over 0.5, but as soon as you get a room with 23 people in it, that probability that 2 people have the same birthday just becomes a little bit more than 50%. So I don't know, walk into a room with more than 23 people. I'm guessing if you bet that 2 people have the same birthday, someone will take that bet, and there's a higher likelihood that you're correct that 2 people have the same birthday, and that instead of that, that there's nobody with the same birthday. So I don't know, I'm just kind of taking some of the things that we've talked about, independence, but also this kind of simplified version of this is going to look very similar to what we're talking about when we look at binomial distributions. Okay, so kind of keep this in mind. This is kind of very similar to a binomial distribution problem, a little bit different, but it allows this idea of allows us to introduce this idea of factorials. So here, 300 and what 25 factorial. So 300 and that would mean I take 325 times 324 times 323 all the way down to 1. Okay. So we're going to look at this binomial distribution, which also uses this idea of factorials. So if I run an experiment that consists of n identical trials, right? So this is going to be our setup for a binomial distribution example. That we're running this experiment, we're doing it n number of times. It has two possible outcomes. So binomial means that I can see two things occur, either a success or a failure. We also need the added assumption that the probability of success is the same across all trials and that trials are independent. So our binomial distribution examples are really when we're dealing with independent events, similar to this idea of the people having the same birthday. So the next question we might be thinking about then is, okay, if I run this trial n number of times, 100 times, what's the probability I see X number of successes? Or, if I'm selecting a person at random and I want to know, are they over 6 foot tall or not? What's the probability that if I ask 10 people, 5 of them are over 6 feet tall? Right? So, excuse me, sorry. So the basic kind of question we're thinking about is, okay, I can use a binomial probability function to find the probability of seeing a certain number of successes out of a certain number of trials. Okay? And you can kind of think about it, that probability should change, right? If I'm running this experiment 100 times, the probability of seeing two successes will be very differently than if I run the trial 10 times. Or sorry, run the experiment 10 times, 10 different trials. Um, Now the equation, it's pretty messy, but hang with me for a second. This will be our binomial probability function. This will tell me the probability of seeing a different number of successes. So here, n, we would plug in our number of trials, x, the number of successes we're interested in finding the probability of, p represents the probability of success in any one trial, q is the probability of failure. Or I can sometimes think about this as, I could rewrite this as 1 minus p. Because if p is the probability there's a success, 1 minus p is the probability that there's a failure. Okay? So I don't know. I often write it this way. I think in the book they use q. I think it makes a little more sense to write it this way. And then, we're just taking things to powers, right? We're using factorials. Once again, this should look kind of similar to what we were doing with that birthday example, right? These factorials mean start with n, multiply all the way down to 1. So number of successes, probability of success in any trials, P. Q is the probability of failure. N is the number of trials. Factorial is this idea that I start with whatever value n is, multiply by n minus 1. So, right, if I had 10 factorial, 10 times 9 times 8 times 7, all the way down to 1. Okay? It's not too bad yet. Oh, just something that we will kind of use down the road and moving forward is that 0 factorial is actually 1. So this will become useful when we start to work through some of the problems. We might need this. Okay. Also, I'm realizing my footers are not correct in these slides, so just ignore them. It's got like lecture 7, lecture 8 on some of this, but it's all similar, right? Probability, random variables, binomial distributions. But here, we'll look at a binomial example, right? So let's say I have a coin, but it's biased. So the probability that comes up heads is not 0.5, but it's 0.4. It's a weighted coin. What's the probability that 4 of the 10 coin flips come up heads? Well, my number of trials is 10. My probability, the number of successes I'm interested in is 4. And then the probability of success in any one coin flip is 0.4. I've got everything I need. I just need those 3 components to then look at my binomial equation. Everywhere there's an n, plug in 10. Everywhere there's an x, plug in a 4. Everywhere there's a p, plug in 0.4. Okay? So nothing too crazy here. Now you can find this factorial button on your calculator. I think often it's under like a math or probability. Every calculator is a little bit different, but like if it's under a math or probability heading or button, that's usually where you'll find your factorial. I'll also show you how we do it in Excel, so it'll make it a little bit easier there as well. That'll be at the end of kind of a separate video where we look at binomial and Poisson examples in Excel. But this would be the equation that we need to get plugged in. Okay. In fact, actually, yeah, we'll keep moving. So this ends up being about 0.25. Okay. What if I had an example where I'm looking at 5 randomly selected adults? What's the probability 3 of them have a college degree? So I know that on average, right, the probability if I select any one person at random, probably they have a college degree is 0.3, right, or 30% chance. So I want to know the probability there's 3 of the 5 people I've selected. So my n is going to be 5. My x is 3. My p is 0.3. I just go ahead and plug those in, and I should get about 0.13. Okay. Now, I'll show you real quick. I will do like a separate one here, but I'll show you how we could use Excel. Make sure I'm still sharing my screen with you. Yes, okay. So, oops, there we go. Let's say I wanted to take, oops, 2, I can type, 2 factorial, right? Well, 2 times 1 is 2. But what if I wanted 3 factorial? Should be 3 times 2 times 1. I should get 6. So that FACT, that's basically going to be our factorial, our exclamation point, right? That's our factorial operator. So if I'm trying to find, that example where the Wall Street Journal, I said, okay, look, I need to take n factorial. So my n was 5. Divide that by x factorial. I was interested in finding the probability of 3 successes, 3 of the 5, and then multiply that by n minus x factorial. So n minus x factorial. I then want to take that entire fraction, multiply it by the probability that they had a college degree, which was 0.3 to the x was 3, and then multiply that by, and if I'm kind of worried here, the order of operations, it wouldn't, but like I can kind of section this off just to make it easier for me to kind of see the different parts of that equation. Oops. There we go. So let's get that out there. And then I'll take 1 minus the probability of success. Right, so 1 minus 0.3 to the n minus x, so 5 minus 3. If I hit enter, I should get 0.1323. So let's go back. This slide's it. There we go. Oops. Here we go. So about 0.13. Okay. What if instead I wanted to know what's the probability of 4 of the 5? Well, here, one thing with the binomial distribution is we can think about as we move further and further away from the expected value of this binomial variable, that we should be getting probabilities that are closer and closer to 0, right? Now, we haven't talked about what the mean of a binomial example or binomial variable is yet, but we'll kind of see this highlighted, and I'll kind of connect these 2 principles here in a second. So if I know that on average, 30% of people have a degree, well, then on average, I could think about out of 5, about 1.5 people would have a degree. So the probability that 3 people have a degree we just found was 0.13. So the probability that 4 of the 5 should be even lower. The only value here we have that was lower than that is 0.028. That must be the correct answer. Sure enough, if we go ahead, rework this, plug in instead x equal 4, x is equal to 4, we get that probability of 0.028. Okay. What is the probability that at least 3 out of 5? Well, now we could start to work with kind of cumulative, right? So at least 3 out of 5 would be the probability of 3 plus the probability 4 of the 5 plus the probability that 5 out of 5, right? Well, we already have the probability of 3 out of 5. We have the probability of 4 out of 5. The only thing left we need is the probability that we have all 5, right? So I went ahead, determined that. Once I add these all up, I get the probability that I see 3 or more of these 5 people have a degree as 0.16. Just to mention though, I had an additional kind of line here because it doesn't make the most sense in this example, but sometimes it's easier to do the complement. So I'll give you an example here. Let's say I had, I don't know, say if I select somebody at random, the probability that they, I don't even know if this is true, the probability that they, I don't know, have at least a 10th grade education is 0.9. I'm hoping it's higher than that, but we'll stick with that, right? And let's say I'm looking at 100 people, and maybe it's okay, what's the probability that out of those 100 people, um, 98 or fewer of them actually, right, have this 10th grade education? Well, that would mean I'd have to find the probability that x is equal to 98 plus probability is equal to 97. I'd have to use that binomial um, equation a lot of times. But if I know that this is event A, I know I can always rewrite an event as 1 minus its complement. Well, what is the complement here? That would be being greater than 98. This is where I need to pay attention to my equalities. If it's, the complement would be strictly greater than 98, which the only possible outcomes then I could see is x is equal to 99 plus the probability x is equal to 100, and that's the highest number I could possibly see. So here I only have to use that binomial equation twice. It's going to make my life a lot easier. So if I ask you a question on the homework or something like that, where you're like, man, I gotta find 25 different binomial, use that binomial function 20 different times, there's probably a way you can rewrite it using the complement to make your life a little bit easier. Okay. All right. So what else do I want to say? Okay. So I kind of alluded to this already, but we can actually calculate a mean and a variance for our binomial distributions. The mathematical proofs of why these equations are what they are, you can kind of go through and look at them. We are not going to waste time on it, but I will kind of explain at least the intuition, especially behind the mean. So I always use these numbers to like, okay, if I had 10 people at random and I know the probability that any one of those people has, I don't know, actual cash on them is zero point 0.2. Well, then out of those 10, how many would I expect to have cash? Well, there's 10 people. Probability that someone has cash on this 0.2, two of them. What did I do in my head there? I took the number of trials, the number of people, 10, and I multiplied it by the probability that any one of them, right, was a success or had cash in their pocket. So that one's, I think, is kind of intuitive. You take the number of trials times the probability of success. And this also makes sense for like the mean is going to be different for different numbers of trials. So if I have 10 people, even if the probability that someone has cash in their pocket remains the same, if it's zero point 0.2, then I would expect 2 of the 10 people have it. But if I ask 100 people, well, what's my mean there? Well, even if the probability that any one person has cash in their pocket is zero point 0.2, now out of 100 people, my mean would be 20. So that mean essentially is like getting larger and larger as I have a higher number of trials, which kind of makes sense, right? Now, the variance doesn't really have that intuition, but our variance, the equation we could use, we take the number of trials times the probability of success times the probability of failure. Once again, I don't like this way, but if it helps you think about it, that's okay. I always write it as kind of Q being 1 minus P, right? So the probability of a failure is 1 minus the probability of success. So the variance can also be rewritten as the number of trials times the probability of success times 1 minus the probability of success. And then same kind of thing applies as we've always been doing. Standard deviation is simply the square root of the variance. So I mentioned this already, but like I'm asking 5 college graduates if they have a degree. Remember, like when we got to the probability of 3, that was a little bit greater than the probability of 4, which is greater than the probability of 5. So here my mean, 5 times 0.1 would be what? 0.5, right? So as I move further from that mean, the probability is going to get lower and lower. So actually, I'll add a caveat to that. Whatever my probability, whatever my mean of my binomial probability function is, The values, the two integer values on either side of it, those two numbers of successes will have the highest probabilities of occurring. And then as we move further from that mean, they decline. So here, the mean is 0.5, 0, and 1 are the most likely outcomes. As I move further from that mean of 0.5, the probability gets smaller and smaller. Here I've got n is 5, p is equal to 0.5. Well, notice when the probability of success is a little bit higher, I've kept the number of trials the same. I get not what looks like a right skewed distribution, but I get what looks more of like a symmetrical distribution. So here the mean would be 5 times 0.5, or 2.5 is my expected value. So 2 and 3 are the most likely outcomes. Sorry. And then as I move further in either direction for higher or lower number of successes, notice that probability is decreasing. Keep the number of trials the same, but I increase the probability instead of 0.5 to 0.9. Now I end up with a left skew distribution. Okay. And then we can kind of just look at different ones. Let's say, here. So let's say I have a higher number of trials and the probability of success is still below 0.5. I still have kind of this right skewed distribution like I did before. Now notice, okay, what's the expected value? Should be 4. So it looks like here, oh yeah, 4. If I get the exact value, that is the most likely outcome. And then as I move further in either direction from that mean, the probability is declining. What if I have another symmetrical distribution where the probability is 0.5, just a higher number of observations? I still have a symmetrical distribution. The mean is 25. That's the most likely, right? That outcome has the highest probability of occurring. And then as I move in either direction, that probability is decreasing. So with a higher number of trials, it looks, same shape of this distribution, but it's more granular, right? We have more kind of bars there to look at. Okay. So back to our Wall Street Journal example. What would the mean and the variance be for this example? Well, the mean is simply take that number of trials, 5, times the probability of success of 0.3. I should have a mean of 1.5. How do I find my variance? Take the number of trials, 5. Where is it? There it is, 5. Multiply by the probability of success, 0.3, and then multiply it by the probability of failure, which is what? 0.7. So I think if I do that, let's see, do I have it here? Yeah, I get 1.05. So also kind of notice the variance of the binomial is actually the mean times the probability of a failure. So just different ways of thinking about this, okay? So in our example, notice I had the mean was 1.5. So that should mean, so I'm thinking about 0, 1, 2, 3, 4. Here's all the possible number of people I could see with a college degree. So if the expected value is 1.5, it should be that 1 and 2 are the most likely outcomes. And I think we had 3, the probability was like 0.13, 4, probability was 0.028, and I think this was like 0.002 or something really small. Once again, my mean, the two values near it will be the most likely, and then as I move in either direction, those probabilities of higher or lower numbers of successes will decrease. In fact, well, I'll hold off on that. Okay. All right, so let me see. I need to share this with you guys again. So which of the following, if we're thinking about when do I apply this binomial, right? So the whole setup was we need independent trials, success failure in any trial, probability of success on any, remains the same on any trial. So what if I was calculating the number of expected number of coin flips that come up heads in 123 flips? Well, it's got my number of trials. These coin flips should be independent. The probability I see a heads in any one coin flip should always be 0.5. It seems like I had really good situation where I could apply the binomial. What if I wanted to know the probability that 5 out of 20 patients will get nauseous from an antibiotic? Well, I've got 20 patients. I know the underlying probability of seeing this negative symptom from taking it, right? And that's the same for everybody. I guess we're assuming that. every person getting sick is independent from someone else getting sick. So I've got the number of successes I'm interested in finding is 5 or lower. I could I could use the binomial here too. And I'd have to use it a bunch, right? I'd probably find the probability that 5 people get sick, plus 4, plus 3, plus 2, plus 1, plus 0. Don't forget about that 0. You can see 0 successes. Calculating the probability that air traffic controllers at the Muncie airport make 3 errors per week. Well, what's my number of trials? Well, I've got per week. I don't know how many. Muncie's a pretty small town in Indiana. I don't know how many people, how many people actually land there. I don't know the number of trials. So C is going to be I can't apply it, right? I've got an open-ended time frame, not a number of trials, which there's another distribution we can use for that. We'll talk about in a second. So hopefully D, we're looking for which one is not appropriate. Hopefully D makes sense. So calculate the probability that out of 5 customers, exactly 3 make a purchase. Well, if we know the probability that once someone steps in the store, that they buy something is the same across all customers. I've got my product success. 5 is my number of trials. 3 is my number of successes I'm interested in finding the probability of. I could success failure, someone either buys something or they don't. I could very easily apply the binomial here as well. Okay. So for that one where we couldn't use it, and we had this kind of time frame, we didn't really have a number of trials. We've got a different distribution we can use to attack those problems, which is the Poisson. Okay. So our Poisson distribution is when we want to know, okay, what's the probability I see a certain number of successes, right? I see, 3 errors being made at the airport, but over a specific time. Now, I'm going to say time. Almost all the examples I'll give you in this class are going to be time. But you can be over a space as well. Excuse me. In fact, I think I have one that we'll think about is a space example, like a physical space, right? So it's physical space or time. What has to be true, an assumption that we make with this Poisson distribution, is that intervals of the same length are going to have the equal probability of occurring. Okay, so doesn't matter if I'm looking at week 1, week 3, week 4, the probability that I see a certain number occur is going to be the same for all of them. I'm also going to assume that none of my time intervals overlap, right? And then finally, the question I'll really be interested in is, okay, how many events or how many successes are expected in every given interval, okay? So I'll show you the function that we'll actually work through some examples. Lambda here is just simply going to represent the mean number of occurrences or successes we see over the time interval, like what the mean is, what the average is. X is the number of occurrences or successes we're interested in finding the probability of over that time interval. And then E, right? So we've got the expected number of occurrences, the number of occurrences we're interested in finding the probability of. The mean number of occurrences is lambda. E is this kind of natural number. You might have seen it in other math classes. So if you take it out to the 5th decimal, it's 2.71828. Usually there's an E natural kind of E button on your calculator. There's also a pretty easy way to do it in Excel, which we'll kind of look at. But if you're just making a rough calculation, keeping out to the 5th decimal should be pretty good. So 2.71828. Right? It actually kind of keeps going. It's like I forget how infinite number of decimals, and you can remember it like out to the 27th decimal, I think, like using Abraham Lincoln facts. Like he was 27 years old and did something. I don't know if it was he elected something in 1828 and 1820, you can kind of go through, but for the sake of what we're doing, we need to know those 5. So this probability distribution function shows us the probability that we see X number of events or successes or occurrences happen over that specific interval, time, space interval we're looking at. So here, what was the setup? So this law of small numbers book, which was written about what now, 130-ish, 125 years or so. I had this example where on average, they were noticing over a year that 0.61 soldiers were dying from getting picked to death by horses, right? The cavalry, right? Some people were getting trampled by their own horse. So we have the average, right? We have lambda 0.61 for our time interval, which is a year. So what's the probability that we have a abnormal year here instead of 0.61 soldier? What's the probability we have exactly 3 soldiers get killed by horses this year? Well, the X we're interested in is 3. Lambda is 0.61. Notice all we need are X and lambda. We always have E, right? So it's just a matter of figuring out what my average rate is over the interval, finding what the probability, of occurrences I want to find is 3. It's just a matter of plugging everything in. Now we still have our factorial. It's getting used here. Same thing kind of applies here. 3 factorial, 3 times 2 times 1. Notice here we're taking it to the negative power. So make sure you include the negative sign here. Otherwise, you will get dramatically different answers. Also, apparently copy pasted and didn't realize. um, Clean that up. So here I get a probability of about 0.02. Just another example we'll kind of work through. Let's say I'm thinking like I work at a hospital and I've got a certain number of births every hour. I'm thinking about staffing decisions, right? So what's the probability that, if on average I have 1.25 births every hour, well, what's the probability I get 3 births this hour? Because if it's relatively high, I don't have the staff to cover it. I need to make sure I ask someone else to come in. This is the setup. I create these ideas in my head sometimes, but this is the kind of scenario. Well, I have my lambda. My average rate is 1.25. I'm looking for the probability there's exactly 3 births, so X is equal to 3. That's all I need, right? Now it's just a matter of plugging and chugging, right? So I get about 0.09 here. Okay. So it shouldn't be too bad. Now, hopefully you can imagine, like I could use Excel to be my calculator here. So I'll Excel open so I can do, in fact, if I really wanted to, I could kind of make this kind of neat. So let's do, whoops, let's make caps lock on. Yeah. N lambda. So this was what we're looking at, 1.25. I don't want N, I want X, sorry. 3, probability that X is equal to X is, oh, now I forget the equation off the bat. So lambda to the X, e to the negative lambda, X factorial. So we're going to take lambda to the X power times, I believe it's EXP. No. Um, I'm gonna kind of do this on the fly. Now I can't remember exactly what the equation is. So I think it's, yeah, okay. I was right. Just want to double check before I do this. So let's go forward here. So I'm gonna take lambda to the X power. I'm then gonna multiply that by this EXP function. If I put a 1 in it, it returns to me that natural number E. It has other uses too, but this is, well, we're not going to use any more than this. So exp1 uses that natural number E. I'm going to take that to the power of negative lambda. I'm then going to take all of that and divide it by x factorial, which I forgot to put in the factorial first. So x factorial, which this is just my Poisson distribution equation. I'll hit enter. Sure enough, I get 0.09. But notice if I set this up one time in Excel, so this might be, I don't know, might be useful to copy what I just did here because I could say, okay, well, look, what if on average I had a much larger town and I had 5.9 births every hour? What's the probability that I get 3? Right? Actually, let's do more than that. What? It seems like it's too low. Oh, it's not. So what's the probability now I see 5 births? Oh, it's relatively high, right? Or what's the probability I see 3 births? Similar to before, but a little bit different, right? Notice 4, it was 0.0932. Oh, it's because I scaled it up. Exactly. Let's do 10 as lambda. Okay, now let's do, I don't know, 7. Now I can play around with these, the probabilities would be a little bit different. Okay. So I could really apply this to any Poisson example, and now all I have to do is change my lambda and x to fit the example. So it might be a nice, useful thing, if you wanted to. I believe I showed you how to do this with the binomial. Well, notice I was using the probability of success here. I could change these to be cell references, right? So maybe instead of like typing this in 5 and 3, what I actually do is say, okay, look, here's my n, x, p, put in the values. So I don't know, we'll just make up some values here real quick. So 5, 3.4. Actually, we'll match up with the numbers. So 5x and 3. Then everywhere I have a 5, I would just put in the cell reference. Everywhere I have a 3, this cell reference. Everywhere I have a 0.3 here. Update this entire thing. So let's see, 5, 3. I'm taking a little bit of time on this, but I think it'll be maybe pretty helpful for you once you start doing this on your own. If you build this out yourself, this will be, I think, very helpful. And I won't give you this function, so this kind of requires you watching this video. But now notice I get the same that value. If I want to start to play around with different values, updates it right away. So that's kind of nice. Okay. All right. So where did we leave off? Too many things open. Here we go. So we did this one, and then I kind of went and did some Excel work. So let's go back and look at this birth rate example. What if now instead I wanted to know the probability of seeing 2 or more births? Right? Well, now I have kind of a problem, right? Because if I want to know the probability of 2 or more, so that's x being greater than or equal to 2, that would be what? So if I want to know the probability that x is greater than or equal to 2, that's the probability that x is equal to 2, plus the probability that x is equal to 3, plus the probability it's 4, 5, 6. I can't use the Poisson distribution, equation to infinity, right? So with the Poisson distribution, it's really going to be important, especially when I want these, like, is it strictly greater than? I'm going to have to be able to rewrite this using its complement. So I know the probability of A is 1 minus A complement. What's A complement here? Being strictly less than 2. Okay, well, what are the only values that are less than 2? The probability that I see 1 birth plus the probability I see 0. Now I only have to use that Poisson distribution equation twice. This seems a little bit more doable. Okay, so sure enough, I go here. Oh, there we go. I rewrite it using the complement. I know that they're mutually exclusive. I can only ever see 0 or 1 births. So those are my only two possible values. I use those x values, the lambda of 1.25. Here's where, if I do need to find the probability of 0 successes, I mentioned this earlier, 0 factorial, we treat as like, it's actually going to be equal to 1. So you have this kind of weird thing with factorials. 0 and 1 factorial are actually the same value, like dividing by 1 here, so it doesn't really change anything. And then I would add those together, subtract them from 1. Okay? So I get the probability of having 2 or more births, 0.355. So we're just kind of combining, a little bit of what we talked about in previous section or chapters with our Poisson example. If we think about different Poisson distributions, we're going to create some visuals. So I just grabbed these from a textbook because I kind of like it, kind of like their example. But as I have higher and higher lambdas or mean number of occurrences, my Poisson distribution is always going to be, right? If I think about when I was giving you an example earlier, the lowest possible successes I could ever see is 0. The highest possible successes I could see, in some situations, if I'm thinking about things that go to the end of time, infinite. So I'm always going to technically have a right tail. Now, the higher that my Poisson mean gets, or the higher that lambda is, right? The higher the mean number of occurrences is, closer it's getting to looking symmetrical, right? But it's always going to have some right skew to it. Same kind of thing applies. So what ends up being true is the mean of my Poisson is just lambda. Like it's defined by the setup of the Poisson, right? Lambda was the average rate we usually see over that time interval. So notice here when it's 0.1, 0 and 1 are the most likely outcomes. The probability declines from there. When the mean was 0.5, 0 and 1 are the most likely outcomes. Well, now notice in both scenarios, they're the most likely outcomes. But when the mean is 0.5, point or 0 is a little bit less likely to occur than when it was 0.1, when the mean was 0.1, and 1 is a little bit more likely to occur than when the mean was 0.1. But then as I move to higher and higher number of successes, that probability is declining. Same kind of idea here. It's just that when I've got a mean equal to 2, 2 is the most likely outcome, and then declines and moving in the direction. San with a mean equal to 5, 5 is the most likely outcome, decreases in either direction. Okay. So similar concepts to the binomial. What ends up being kind of nice is that the variance of the Poisson is simply lambda as well. So it's just really the kind of weird mathematical, I don't want to say anomaly, but if you go through that probability mass function and you calculate, if you use that function, the values that it creates, what would the variance be? It ends up being lambda. Right? So then our standard deviation is simply going to be the square root of that value. Okay. So this is, I don't know, I guess makes it easier to remember. I'll give you formula sheets prior to exams and things like that, but makes life a little bit easier here. So I want to kind of tie in the Poisson to the binomial because I think it's interesting also to give you an example where we're not thinking about well, it'll make sense when I get to that. So let's say I've got 10,000 atoms, right? So I know that the probability that one of these atoms decays over a minute is about 0.0005. Okay? So if I'm thinking about over the next minute, what's the probability that 3 of these 10,000 atoms decay? Okay? Now, it's going to seem stupid to set up for a while, but stay with me. Right? So if I try to use the binomial, which I could, because I've got the probability of success, I have the probability of success is 0.0005. I've got a success or a failure. It either decays or it doesn't. Here it's kind of weird because decaying is defined as our success. I want to know the probability that I see exactly 3 successes, and my number of trials is 10,000. Now, I could do this. Now, if I try to enter this into my calculator, it'll be like, I can't do 10 million factorial. But notice, if I were to write this out, I don't think I have this in the slides, but I think it's worth showing. So like, let's say I had that 10,000 factorial, 3 factorial, 10,000 minus 3 factorial. That's just the first part of it. If I put 10,000 factorial in my calculator, it'll get mad and will yell and it won't work. But notice if I rewrite this, so this is what 10,000 times 9,999 times 9,988 times 9,977, etc. 3 times 2 times 1. And then this is what 9997. So times 9,997 times 9,996 all the way down to 1. Well, notice everything from here down, right? This was times 9996. Everything would cancel. So I'm really just left with 10,000 times 999,000 times 9,998 divided by what? This is 6. I can do this with my calculator. Okay. But that's annoying. It's annoying that I have to figure out, okay, what cancels and go through this whole rigmarole. Instead, what I could do, I can figure this out. Like I said, I can simplify it down and be able to get that probability of 0.14. Or I can use a little shortcut. So if I have a really high number of trials, like it's really, really, really large, I can treat this like it's a Poisson, right? So if the probability of success is relatively small and I have a high number of trials, I can actually use the Poisson distribution to approximate the binomial. So if this is the case, I'll figure out what lambda is by taking the number of trials times the probability of success. I can then use this lambda to find the different probabilities of different numbers of successes, right? So, I'm not going to go with the mathematical proof, but we can show that it's a really close approximation off at I don't even know what decimal, but pretty far out. So if we go to our example, we can think of, okay, there was 10,000 atoms, really high number of trials. Probability of success is relatively low, 0.0005. My mean number of atoms decaying would be what? N times P. So 10,000 times 0.005 or a lambda of 5. I then say, okay, what's the probability that 3 atoms decay? Well, use my lambda of 5, use my number of successes as 3. If I go ahead, plug this into my calculator, I get about the same thing. Out to the 5th decimal, it looks no different, right? Now, it is, will be different. So, if I'm looking at this, oh no, I do want to keep sharing. Sorry. I just want to hit exit and open Excel. So if I do what? 10, actually, here, I've got it all set up. So I could do 10,000. Notice it doesn't like that, but hang with me. So like if I try to do 10,000 here, notice my factorial it doesn't like that, right? But we said we could simplify it down to being 10,000 times 9,999 times 9,998 divided by 6, right? This is what it simplified down to for our, well, maybe. Well, 1,000 times 9,000. Oh, because that's only the first part of it. Sorry. It's like, wait, what? So this is my numerator. That would be times 0.0005 the 10,000. And or to x times 1 minus 0.005 to the n minus x. Nope. I forget. Yeah, this was 3. We were looking at 3 atoms decaying. So I typed that in. There you go. I got 0.1403660. Pretty close, right? If I used the Poisson, right, where I used, okay, take n times p, right? So in this case, I'd say, okay, let's take 10,000 atoms times the probability any one decays. So 5 is, or sorry, I put that in the wrong cell. Lambda is going to be 10,000 times 0.005. I'm interested in 3. Notice, oh yeah, this rounds up to 0.14037. So does this. But if I go out one more decimal, they are a little bit different, right? So it's a close approximation. It's not perfect, but it's really close. And we don't have to deal with those annoying factorials. Notice even here, I had to use a simplified version because if I tried to use my old equation and I use that really high, that factorial equation can't do that. Okay. All right. So let's go. We're almost through this. So we went through this example. Think about different cases where we can apply the Poisson. So if I'm thinking about the number of accidents that occur on a given highway over a day, well, I could look at previous data. What's the average number of accidents I see? That's my lambda. I want to know what's the expected number. Lambda is my expected number, or the probability I see 5 accidents, x is 5. So that one seems like it works. The probability that stock return exceeds 10%. Well, this is, I could phrase this one differently, but the probability that it exceeds over 10%, it's not like I can phrase that as a success failure, right? Because I could see not just 2 outcomes. I could see a stock return of 9,000. I could see a stock return, sorry, 9,000, 9%, 11%, etc. So this one doesn't really make sense for us, right? Because it's not just a success failure. We could see it stock return being 11%, 12%, 13%, all kinds of values. The other two should then hopefully make sense. But yeah, the probability I see a certain number of calls to a call center in a given minute. Once again, I could look at historically how many calls my center gets per minute. That's my lambda. I want to know what's the probability I see 10 calls this next minute. That's my X. Probability I see a certain number of insurance claims over a month, a year, some period of time. Once again, I have a lambda of the average number I usually see, number of claims I usually see. X would be just the number of claims I'm interested in finding the probability of. That one I could apply to as well. Okay. I've then got one more example that we'll work through. And I wanted to give you one where it's not time, but it's a physical space. So go back to this guy. I forget, William, I think his name is something Gassett. I should know him, and we'll talk a little bit about why I don't. But he was a brewer in 1899, no formal training in statistics or education in it. But he discovered in working in this brewery that the number of particles, and I believe it was yeast particles per milliliter in this beer, followed a nice Poisson distribution as he sampled it, right? So you brew beer, these massive vats, like if you're distributing it, you can't test the whole thing to make sure it's got the right number of yeast particles. You can only test like a milliliter at a time, so you're not wasting a bunch of your product. So he figured this out. He also made tons of other discoveries, like in statistics, and none of them are given his name. So we'll talk about the Poisson distribution. Um, guy's last name was Poisson. He came up with it. There's other distributions that are named after that person. We'll talk about one later on this semester, which is called the normal distribution, often the Gaussian distribution. Last name was Gauss. So unfortunately, his discoveries, because he didn't have any formal training, he didn't have like a degree from one of these Ivy League, they just called them student. So there's actually a set of distributions we'll use called the student T distributions. It's referring to this guy Gassett, right? So maybe I should, just to be nice, start calling him Gassett. But he made a bunch of money. Smart guy. So the example we're going to use, enough of that, is let's say I was testing, right? I've got this huge vat of liquid and I'm testing the yeast particles per milliliter. So I draw out 1 milliliter and I see that there's 10 particles, okay? What's the probability that in the entire liquid that I see exactly 8, right? So my sample, right, my 1 milliliter sample is going to be my best idea of what the average number of yeast particles is. So I'm going to have kind of my average number being 10. My lambda is 10. I then want to know, okay, man, I saw 10 from my sample. I'm really hoping that's only 8. So given that I saw this average number of particles in the milliliter I drew out was only 10, what's the probability in the entire vat? It's actually 8. Because that's what I was targeting. Well, that probability is relatively high. So what's lambda? I just said, right, was that sample we took, 10. That was the average that we saw. The number of particles we're interested in find the probability of is 8. Now notice, we're not looking at time here. We're looking at a physical space, milliliter of liquid, a volume, right? I then kind of think about, okay, I could plug and chug, pun intended here, right? But lambda is 10, x is 8. Just a little bit of work to show that that probability is only 0.11, right? I don't know. It's kind of a way of introducing some stuff we're going to talk about down the road with the student T distribution, but also giving you an example where we're not looking at time, but physical space. I could also think about other ones where it's something like, what's the probability that I see 5 pieces of trash on the next mile I drive on I-69, right? I know the average number of pieces of trash I see driving a mile on I-69. If I drive on there today, what's the probability I see 5 pieces of trash in that first mile, right? So that, once again, it's not a time example, it's a space, not a volume of liquid there, but a length, right? A distance. Right? All right. And then we'll kind of end this with some kind of corny stats joke for the video. Have you heard the joke about Poisson distributions? It's pretty fishy. Poisson means fish in French, so yeah, it's a bad one. Let's be honest. So I've got these at the end. I'm not going to walk through them. I'm actually going to do a separate video where I show you how to use the built-in Poisson and binomial distributions. But these will be some of the reference slides you can use.